Hello, my name is Matthew Serber, and I'll be helping you learn AP Chemistry through Peervids. So, this is Unit 1 in the AP Chemistry Barron's book. I have the 6th edition. If you get that edition, it'll be easier for you to follow along. So, on the first real thing that they try to teach you is some famous scientific discoveries. So, 3 main ones to know, because there are often multiple choice questions on the AP test. You get some easy points there. Is the 3 I have here. Millikan oil drop experiment. He conducted electricity through a wire to attract oil and used that to discover the charge of an electron. Next one is the Einstein, light is a particle and wave. It was an experiment Einstein did where he discovered that light often acts as a particle or a wave, not one or the other all the time. And the final one is the Rutherford gold foil experiment, where they launched a bunch of atoms at gold foil and they saw, based on how they bounced around, whether where the mass is concentrated in an atom. Alright, the next section of Chapter 1 in the Barron's book refers to the parts of the atom. Very easy. As you can see, protons and neutrons and electrons, I gave you little P's, N's, and E's because that's how they'll often be referred to in diagrams, especially like electron. It also can be like an E with the minus sign next to it to show the charge, because later you'll have to deal with positrons, which would be E with the plus. So anyways, not important, but the main point is protons, nucleuses, they make up proton and neutrons make up the nucleus, and the electrons orbit around the outside, what's called the electron shell or the electron cloud. Alright, the next section of Chapter 1 is about wavelength, frequency, and energy of light. It's more physics than chemistry, but some of the equations will be pretty important and applicable later in chemistry, so you need to learn it. It's a big part of chemistry. So one of the main ones you get is this little guy right here. You get this pencil tool, you get a little lambda, which is wavelength, and they use a V, and the V isn't velocity now, which you would think for physics. V is frequency, so like hertz, megahertz, and so wavelength times frequency is going to equal C for all the electromagnetic spectrum. All the wave frequencies on the electromagnetic spectrum. And in case you don't know, C, real easy, is just 3 times 10 to the 8th, I think, meters per second. And that's the speed of light, so that's pretty easy. And another really important equation is it's very similar. It's HV equals E, where E in this case is the energy of the wave, and V is still the frequency, but H is short for the Planck's constant, which will be in your AP booklet, so you don't need to memorize it, but just so you have an idea of what it looks like, it's 6.63 times 10 to the negative 34 joule seconds. That's pretty small. There you go. So, pretty easy so far. Guess we can do a couple examples. I mean, it's mostly just plugging in, so yeah. Alright, as promised, here's an example. So, if I told you a certain wave had a wavelength of 400 nanometers, and I asked you what the frequency was, just plug it into your lambda frequency equals speed of light. So you got 400 nanometers times frequency equals 3 times 10 to the 8th. Pretty easy stuff so far. Sloppy 8, sorry. I don't really have anything to write with. Then you gotta convert 400 nanometers into a normal unit, into meters, right? So that's gonna be 400, and so nanometers is 10 to the negative 9th, so you get it times 10 negative 9th meters, because nano prefix. Another important thing to learn for chemistry is know your units. That equals 3 times 10, 8. And then you just do some dividing, right, over C, and you get what number? You get C, or you get frequency equals 7.5 times 10 to the 14th, and then 1 over seconds is how you write that. -1. There you go. There's an example. Very easy to do. Pretty self-explanatory. Alright, the next topic in this section is the Bohr model of an atom. It's very simple. It's just nucleus. Here, let me move that to the middle more. We're going to go nucleus, and we're going to go, and it's just layers of electrons on top, just different electron subshells. So you get 1, I don't know, maybe 2. We'll try to put like 4. There you go. Usually like the standard model has like 5. We're kind of running out of room, so we'll just do 4. And so each electron subshell requires a different energy requirement of an electron to move up to these levels. So in a ground state of where there's like no energy being put in, of like a hydrogen atom, it's just going to have an electron right there in the first level, just because there's no energy putting in. It naturally stays in the first level. But if you apply some energy to it, you could solve for it later. You'll learn how to do that. It jumps from the second level up to the, or from the first level up to the second level. And so, as you can pretty well see, I mean, it's pretty easy. It's just different levels. And to move the electrons around, all you have to do is apply energy and jump them up the levels. So later you'll learn different. Oh, there's the picture on the next page. I'll just draw that in the next slide. But you can see how much energy it takes to move up to each level using a diagram. You'll see in a second. Alright, so here's the aforementioned diagram. So normally they'll put like 3 different series on here: the Lyman series, the Balmer series, and the Paschen series. But just for simplicity and room, I'm just gonna have Lyman series. So each of the series have a different amount of arrows. The Lyman is the only one that has arrows that go all the way down. But the main point of this graph, the numbers in, is it shows you the energy requirements to get up to that. And so as you can see, I'll just explain as I'm writing these in. The numbers are not evenly spaced out. That's because as you get to higher energy levels, become closer and closer together. Now, there's a couple things that contribute to this that you probably don't ever need to know, and I'm not going to go into right now for certainly. But these number differences get smaller and smaller, and so as you get to higher subshells, it becomes easier and easier for electrons to jump up and even be in the second level in the ground state. So yeah, I guess I'll just stop with these numbers. You don't need to memorize them or anything. They're just there, and you'll always have a table around if you need to solve for what level something's in or moving to. So one of the things that they cover in the book really fast, tiny section, so I'll just do it really fast, is that the momentum of an electron is related to the size of the electron orbit. I'm just putting this equation in just so you can see what sort of relationship it is, but it really is not a big deal. I've never seen this. It's new to me. Never went over this in my course, never needed it on the test, so it looks pretty easy. You just plug the numbers in, but I doubt you'll ever need it. Alright, so we're about to get into the quantum mechanics chunk of chapter 1. So, just explain a couple things really fast before we get there. So, from the videos, or the slides already covered, we know from like the Bohr model, just because it's the simplest, there's a nucleus, there's different subshells. And so, like I said earlier, in like a hydrogen, there's 1 electron. Well, each subshell can only hold a certain amount of electrons. So, hydrogen, real easy, just 1. That doesn't even fill up the shell. Well, the first shell can hold 2. So helium, it being the noble gas of the first row, it has a full electron shell. This makes it very stable. The next noble gas is very stable, is neon. This is because the second row holds 8 electrons, and neon has 10 total, so it has a full first shell, full second shell. Now, after neon, I'm not sure which element it is, but I believe it goes 8 again, so do that. And then after that, I think the shell jumps up to 18. So the reason that noble gases are so stable and tend not to react very much is because their electron shells are full. This makes them very strong, and because they don't need to add more electrons or take any away, it makes them not likely to react with other elements. Alright, so now we're getting to the end of chapter 1 pretty much in the Barron's book. If you are in the same edition as me, I'm now on page 90. There are a couple tables that you'll want to be looking at just because they're a little big for me to draw on the page. They're pretty handy. So I'll just explain this really fast. The different sublevels hold a different amount of electrons, right? Well, the way people keep track of these electrons is they give each one a specific its own place. So first sublevel can only hold 2. Well, the first level can only hold 2, and each level is made up of subshells. Probably should have said that first, but first level, the first subshell is called S. So in the first level, so you can have one electron rotating one way and one electron rotating another way. You can't have 2 rotating in the same direction. So that's the only reason you can have 2 per area, I should say, of the subshell. Anyways, so then you up jump to the second level, and then that has another S, because the first level of every subshell is an S, and the second level is a P. So P, you get S, so that's, I should not do that. I should fill it in the right way, not the lazy way. Don't learn from me, I'm bad. Alright, so that gives you a total of 5. So now, electrons like to fill up one shell at a time. Now, you can't really see this from my drawing, but P is above S. So S needs to fill up all the way. So this would be the atom with 4 electrons, number 4 on the periodic table. And number 5, you probably can guess, the first electron will go right there. And number 6, you might not be able to guess this because it's kind of counterintuitive. It's going to go right there. Instead of filling up one all the way and the next one all the way, electrons each tend to take their own spot first, so they don't need to share if it's not necessary. So then the third one, or I should say 1, 2, 3, 4, 5, 6, I should say 7th element, is going to take that. Now the 7th element, this makes the 7th element more stable than the 6th element because there's 1 electron in each of its subshells. So when you get to ionic bonds, or not ionic bond, when you get to ionization energy, you'll see that it tends to go up as the nucleus gets bigger, but there's some irregularities because of this effect, because electrons and atoms are more stable when there's 1 in every subshell. So then the next guy right there, that's number 8. I think that's oxygen. He's gonna be less stable than than number 7 was before it, because now he doesn't have a balanced. Right, so now this guy, this is number 8. It's oxygen. He's even more well balanced because all his subshells are filled, and he has a complete one. But of course, the most stable will be neon. This is neon again, just because it has full electrons in all its subshells. To get neon to react and take on more electrons or lose one, you either have to tear one away from the full subshells, very hard, full subshells are very stable, or add one, which you can't really do either. There's no more room. So, yep. Alright, now, you see I've added to the little table that we had before. The third sublevel letter is always D. So, as these fill up into the third row on the table, and electrons start going to the third sublevel, you start seeing D. But, well, D is made of a couple levels, but anyways, as you start filling up, you can see D is above P. It's a pretty big difference right there, bigger than the one between S and P. I suppose it's kind of hard to see from my drawing, but later, as you add more and more electrons, and you're farther into the table, you'll, the D will be actually part of the next row, a good chunk of it, which is why you only have another added 8, because you get that. I botched that. Alright, so this is another very important factor in the electron subshell. So, as you can see from my drawing, sorry it's a little sloppy. I'll separate that into little levels for you. So, what you're going to start seeing here is that they all start with the same levels, right? D is the letter that represents the third sublevel. But, so, as you fill in these electrons, you get 2 here, so that goes to helium. You get another, because P is made up of 3, and that one's going to be 5. Let me erase that. Yeah, that's not 4. Alright. So as that starts to fill in, you start seeing the big out of electrons. Well, S and P, that's 4 levels. 4 times 2, 2 per, right? It's another 8. So that's why neon is 10. Has 10 electrons. 2 plus 8. Makes that a very stable gas. Well, the next one only goes up by 8 because this is going to be a little weird, so bear with me just because it's a weird rule. D is so much above P, it's in the next level. You count D in the fourth row, so you don't see any electrons that are in the D sublevels until you're in the 4th row on the table. So you get just another plus 8 right there. So this will keep happening. So if you pretend with me that the table continues down over here, you get 5. Well, 4 is going to have its own S and P. Should make that clear. So that's why the S and P. Now, if you count the S and P and D of 4, you get 18. So that's why that goes up by 18. But now I know what you're thinking. You're thinking, what about the D level of 4? And the next sublevel that comes with that, D. Well, the next one that comes after that is F, and after that it's all alphabetical. So 5th one will go S, P, D, F, G. But those, each sublevel jumps more levels than the one before it. So D jumps 1 up, that's why it's up there. And then level 4's D will be in level 5. So it'll have its own S and its own P, and then you'll have level 4's D right there, but it's F, but then level 5's D and F. Level 5's D is going to be in the 6th level, and level 5's F is going to be in the 7th level, so you don't really see them ever. It's a very weird concept, but it is something you need to start wrapping your brain around to understand the periodic table better and to understand electron stability better. So, yeah, just, I guess, keep working at it in your brain. I apologize again, my table's very sloppy, not that great, but I'm sure your book has a much better one inside. So as you start referring to each specific electron, each one gets their own numbers. And so you'll probably have a nice little table in your book that will tell you I'll give you a column, something like N, and then what sublevel number? That'll be L. And then you'll get the sublevel letter. We'll just put letter there, and then you'll probably get some, like, it's called ML. It's not called ML. It's written as ML. It's magnetic. It's the magnetic quantum number. So it's a little weird, but these four numbers are all related. We're just gonna go through that. So N is the subshell level. So in the first row, one subshell. Now you start at 0 for L. So there you go. L comes in 0. Subletter of that is going to be S. There's only one. Now ML is going to, the magnetic quantum number, is going to be equal to the positive and negative values of L. So the ML for the first row will be 0 because you just have 0. Well, if N is 2, now it counts up. So now you have two numbers in L. You have 0 and 1. Just think of it as counting up, starting with the number 0. But now you have access to your second orbital. So you have another S. Now you have a P involved. Just gonna do lines, kept that separate better. Alright. Now your ML is going to be plus or minus 1 and 0. Or negative 1, 0, 1. It's just important things to know so you can refer to specific electrons within an atom. This wasn't a huge part of my test personally, but unit test wise it was very important. But for the AP it was not as big of a deal for me. But as you can see, we'll just do one more, get the D going. Alright, so if you could guess what L would be, it's going to be 0, 1, 2, and that's that. Alright, and then S, P, it's got those orbitals again, and now it has the D orbital, which it technically takes place in the 4th energy level because D is just way up there. And because the energy levels get closer and closer together, which I mentioned earlier, that's why when D is raised, it starts bleeding into the 4th energy level, because now 3 and 4 are too close together to accommodate a 3rd sublevel or subshell. Yeah, sublevel. Alright, and so ML, -2, I'm just going to write it out so I can explain this next concept really fast, or better. So you can see here 5 numbers that ML could be, and that's why D has 5 blanks to fill with electrons. M, oh, the P orbital, P has 3, right? Well, as you can see in the second row, when P is introduced, you have 3 numbers, -1, 0, and 1. The first column, only S, only has 1, because it only has 1 ML number. So, it's a little connection. I'll hopefully help you keep it organized in your brain. Alright, at some point you will probably be asked to refer to a specific element by its electron configuration. So, this is just pretty much listing all the electrons that are in this element. So if they ask you to refer to sodium, let's say, we know sodium is the first element in the 3rd row. I think that makes it number 11. So, how's the first row fill up? There's 2 electrons, right? So you're going to say 1s. 1 is referring to the first row, or the first level, energy level, and then the S is to which sublevel it is, and then the 2 is how many electrons are in that one. So now sodium's in the 3rd row, so we're going to have 2. 2 has its own S again, right? So then you get another 2. There's another 2 in there. And 2 also has its own P level. And how many electrons go in P? It has 3 blanks, right? So 2 per blank, you get 6. Now, electron, there's one more because it's number 11. So it's the first level that comes up in row 3. It's S again. And how many electrons are in it? Just 1. Now, if I had asked you to say what the electron configuration for a sodium plus ion, it would be when sodium loses 1 electron, right? Well, That's going to be 1s, 2s2, 2p6, and no 3s1, right? Well, we lost the 3s1 that's right there because that's the electron that sodium would lose. It's the only one by itself. That's the one that gets ripped off. So now you don't even need to write the 3s there because there's no 3s1 anymore. Now, if you start practicing this, you'll realize that that guy right there is also the same electron configuration as neon. So that might come up, might not come up, but if you are writing later ones, like much farther down the table, I know, like for just sodium again, for an example, you are, some people will allow you to just put neon and then 3s1. Kind of ran out of room there, but the neon in brackets, the neon sign, shows that you know the noble gas that came up right before, or the nearest noble gas to your element. The neon in brackets represents all this ick right there. It's a lot of writing just to do for sodium. So, and then the same way the next noble gas would represent all of that plus 3s2, 3p6. So, there you go. Pretty easy, just learning to practice how to configure your electrons and how to write which element is which. This is just a side note. There's not a lot of teaching for me to do right here because it's not horribly important, but later on in the table, when you start getting to like the 4th, 5th row, you start getting some abnormalities in your electron configuration. So, like copper, for example, we'll use our abbreviation for the configuration, and then we'll go 3s2, 3p6, and we're in 4s now, right? Well, here's where it gets weird. The way copper is, that's a D, by the way, sorry if that's hard to read, and that's copper, Cu, sign for copper, is, and that gets 10. So remember, the D row jumped up to the 4th level. Well, as you can see, D goes above 4s, but it's below 4p. So it's one important thing to know from this. But the second big takeaway is, you might notice this guy right here, the 1. Normally, electron shells, they fill up all of them at once, right? You'd think there'd be a 4s2 and a 3d9. Well, the D row is more important for the D row to be filled all the way because now you have 5 completed subshells. But it's kind of an obscure reasoning, and I don't really want to get too into it because it's not super important, but you will start to see some abnormalities, and it just has to do with the most efficient way to fill up the electron shells in a way that makes the atom the strongest. Like, if you look at silver, it's pretty much a row down, and it's the same. It goes 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s1, and then 4d10. It also has a subshell that's incomplete in the middle of it, which is unusual. It happens very rarely, but it does happen more often as you get later in the table because the energy levels get closer and some of the levels like to fill up first. Alright, the next important thing that your book covers is counting valence electrons. That's an extremely important skill in AP chemistry because it'll help you a lot when you start having to draw bonds and see how chemicals would react with one another or write out certain ionic compounds. But anyways, the valence electrons, they are the electrons that are on the outer subshell of an electron, or of an atom, sorry. So, that's the laser pointer. Alright, there we go. Here's the pencil. So when we drew our hydrogen atom earlier, it had a nucleus and 1 electron, right? So you would say it has a valence electron. It only has 1 valence electron. Well, if we go down to neon again, what do we say? It has 2 in the first shell, has 8 more in the next one. That's probably about 8. Yeah, that's 8. Alright, anyways. So, it has 8 in the next one. Well, how many valence electrons does neon have? Neon has 2 plus 8. It has 10 normal electrons. Well, there's only 8 electrons in the outside of it. So, it has 8 valence electrons. The valence electrons also, another way to look at it, if you have the configuration, electron configuration that we just had in the last slide drawn out, is the valence electrons are the electrons in the highest s and p orbitals. So I'll say that again. They are the electrons in the highest s and p orbitals. This will be true for any row. So if we looked at copper again, I had that drawn out last time if you want to go back and see what it looked like, but you would say it only has 7 valence electrons because it only has 1 valence electron. I'm sorry, it has 1 valence electron because 4s is the highest s orbital, and then there's no 4p orbital yet in there, so it only has the 1 electron from 4s. So copper would only have 1 valence electron. I should say highest s and then matching p orbital. It's matching of height, not then the highest p orbital that they have. It's the highest s and matching p orbital. Alright, just a quick review of quantum numbers, and then we are done with chapter 1. Well, the quantum numbers, we talked about this a bit earlier. There's one called the principal quantum number. Principal quantum number is n. And as we referred to earlier, n is really easy just to think of what subshell it is, like what energy level in the electron that it is. So hydrogen, you're probably going to think mostly in terms of n being 1, because it only has one level of electrons, whereas in something like neon, you might think of n as 1 and 2, because it has 2 levels. Alright, the next number is a little cursive L that we saw earlier. Now this is a kind of obscure name. It's called the azimuthal quantum number. And this is, once again, it's numbers counting from 0, this is including 0 from, this is the counting from 0 up by 1 from n. So if n is 1, L is 0. If n is 2, L is 0 or 1. It's any number lower than n that isn't negative. Alright, any whole number, I should say. The next one was M, L. So this is the magnetic quantum number, is the professional name for it. And this is equal to any number between negative L and positive L, any whole number, including 0. So if n is 2 and L is 0 and 1, that makes ML negative 1, negative 1, 0, and 1. So I'll just fill that in for you so you can follow along better. Now, the final number is written as MS. This is the spin quantum number. And this is, it's only ever going to be negative half or positive half. This is because the electrons can only spin in opposite directions. They can't go the same direction, so the electron spinning is one or the other. Now this way you can refer to a specific electron in a specific shell. So if I said the quantum number, if I'm looking for the electron with the quantum number n of 2, L1 and ML positive 1 and MS positive half, you would tell me that it's in the second, right? It's going to be a 2 something. Now L, 0 or 1, 0 would be S, right? In this case, and that would be P. So it would be 2P. Remember, if P has 3 spots, well, 3 spots can be represented on the ML as negative 1, 0, and 1. So ML of 1 is going to be one of these two. If I told you it's the positive half is MS, then it's going to be the one spinning that way. If I told you negative half, it'd be the one spinning that way. So you can use these quantum numbers to refer to specific numbers or specific electrons inside an atom. So it's
a lot to take in, I know, and I even don't think it's super important because I never had to refer to specific electrons on my AP test personally, but it is a good concept to know and understand, especially if you're considering chemistry or physics later.
And that's it. That's chapter 1.